Okay, so shall I start now?
Yes, yes.
Yeah, so if we load the package extras and then we suddenly see that there are this, like for example, if we just try searching killing, so it tells us about like killing vectors of. So what this command does is it defines that a particular tensor is a killing vector of some metric. Then if you search more, for example, killing vector q, so what it says is that if it checks whether a given vector is a killing vector or not. So I think if one digs deeper, they can find out whether given a metric, whether a vector is a killing tensor or not. But the question, inverse question, I do not know how to answer. Like, given a metric, how do we really go about finding out killing vectors? Maybe the answer already exists. That I do not know. The second question was about tetrads in xAct. And here there indeed is a package called but other than Mathematica, there is another computer algebra system called Cadabra, and that takes care of tetrads and tetrads. The older version of Cadabra, called Cadabra 1, had all of its functional. The newer version, Cadabra 2, still has to like upgrade these commands. But Cadabra, nonetheless, is a very useful software as it allows much more flexibility to the user. But there, the user has to work a little more to define to get their work done, because many of the things are not that automatic. But then it allows more flexibility. I mean, so many things which are not possible in xAct can be done. Finally, there was a question about working with covariant derivatives, which when acting on a metric do not vanish. So is it possible to program such theories in xAct? After a bit of search, I could not find such a thing, because xAct perhaps requires matrices to be metric compatible. But maybe this is just my limitation. Maybe the question can be raised in the xAct Google forum, which is. And finally, there was one issue about showing how to obtain equation of motion for higher order gravity theories using extras. This was left yesterday. This we can go back again. Anyways, I'm sharing my slides. So if one is interested, they can directly learn from there. It's a very simple thing. But let's continue with today's talk. If there is time, we'll get back to this. Okay, so with this, let us start today's session.
Yeah, Sitender.
Yeah.
Maybe we can take one question if you have looked at it. So this is relevant to this.
How is it? So
can't you do the tetrad calculation in xAct or something?
It can be done. It can be done. As I mentioned, this.
Okay.
There is a package called npghp. So this is the link. Here you can find the documentation. So there I can see that there are tetrads, etc. But maybe not of very much generality. Maybe there will be some restriction. Okay. So that's
okay.
Yeah.
Go ahead.
See is how we can use xAct to learn some physics in Bondi gauge. So in this session, we present some of the details of how we can use xAct for computations involving Bondi gauge. We shall be following three references. The first reference is aspects of BMS CFT correspondence by Barnich and Trossard. The second is the lambda BMS4 group of DS4 and new boundary conditions for ADS4 by Jeffrey Compere, Adrian, and Romain. And the third paper is the partial Bondi gauge further enlarging the asymptotic structure of gravity by Mark and Celine. Yeah, so these are the primary references that we shall be using. Now, so programming this in xAct involves two steps. The step one is essentially to verify the results of the Christoffel connections and the Ricci tensors that have been given in this first reference, so that we also get a handle of whether it really is programmable in xAct or not. So this is our first goal. So yeah, so let's just briefly recall what Amitabh already mentioned in his first half of the lecture. So the metric in the Bondi-Sachs form is of this form. Here we see that there is no GRR component or GRA component. So these are like three equations. This is one equation. These are two conditions. And then there is the fourth condition, which can be written in two equivalent forms. This form is called differential form, and this is algebraic form, where we demand a certain property on the determinant of this round or this two-dimensional metric along the x direction. Now the point is, any metric can be can be brought in other form. The transformations might be very hard to get, but this is a general result. Any four-dimensional metric can be brought in this form. In the above, beta, v, ua, and GAB are arbitrary functions of the Bondi coordinates u, r, and xa. Further, this additional condition, this metric condition, essentially implies that CAB. Okay, I think I see. So here I should mention that there is this expansion of this GAB can be readily expanded, and yeah, this can be readily expanded, and the determinant condition on GAB then forces certain relations among these objects D, E, F, and these are all rewritable in terms of C and E, etc., etc. So these are some of the conditions. I mean, to begin with, these things are arbitrary, but determinant condition implies, for example, that CAB, this guy, is traceless with respect to QAB, and that DAB is related to CAB, and there is a trace-free part. So this curly D. Similarly, E is also related to curly B and C, so on and so forth. So yeah. Now, so this is one thing. So we expanded the metric like this. What about the other fields? So for the other fields also, as Amitabh has mentioned, we will expand them in one powers of 1 over r. So for example, beta is beta naught plus beta 1 upon r, beta 2 upon r squared, beta 3 upon r cubed, and so on and so forth. Similarly, UA can be expanded as U0A, U1A upon R, U2A upon R squared, and so on and so forth. Finally, V can also be expanded in powers of 1 over R, V0, V1, V2, V3, etc., etc. Now, so with these expansions, our goal is to substitute all of them in the Einstein equation, which with some cosmological constant term, lambda, and demand that the Einstein equations are solved order by order. So so the idea is not all all these arbitrary tensors CAB, DAB, E, beta 1, beta 2, beta 3, U0, U1, etc., etc. All of them, if we demand them to be arbitrary, these equations will not be identically zero. And demanding that Einstein equation do get solved, they fix some of these functions, like for example beta 1, beta 2, or they relate these quantities among themselves, as Amitabh had already mentioned in his talk or showed in his talk. In this talk, we will see, for example, how we can get those relations explicitly by making use of xAct. Yeah. So now the point is, if we naively, very naively, just give it to Mathematica and ask, I mean, substitute all of these equations in all of these equations, and then say brute force just solve it, it will not be able to do that. If there is a supercomputer really really powerful, maybe it might be possible, but it's really complicated. So what Bondi and collaborators came up with is something called the Bondi hierarchy. And in Bondi hierarchy, what it says is that there is an order of solving the equations that simplifies the determination of solution space. So let me very quickly recall what are the equations that we need to solve first. So to begin with, so there are like these equations. So equation involving GUU, GUR, GUA, GRR, GRA, and GAB, all of them equal to 0. So the idea is to first solve the equations that do not involve these lambdas, which we can see from here is GRR and GRA. So the first equation GRR solves for beta, and the latter solves for UL. Latter means this GRA equal to 0. Integration of the second of the above equation, that is GRA equal to 0, leads to an integration constant called Na, and this is interpreted as the angular momentum aspect. The time evolution of this Na is determined by another equation in the later in the Bondi hierarchy, which is GUA plus lambda GU equal to 0. So having solved, gotten the contents from the equations that do not involve this cosmological term, we solve for lambda dependent equations of motion. So first we solve for GUR, this guy, equal to 0. And its contents are same as GAB, this equation, as Amitabh has already mentioned in his lecture. But the point is, these equations give rise to another integration constant called M, and which is interpreted as the Bondi mass. Finally, having dealt with two of these equations, we are left with just these two equations, GUU and GUA. The former, this guy, determines the mass loss formula, and the latter, this one, determines the evolution of angular momentum. Now, this is essentially the theory, and we need to implement this in xAct. As we can see, the situation is neither fully covariant nor fully coordinate dependent, because it is not fully covariant because we are not using full four-dimensional indices. We are mixing things up. U is there, capital A is there, and R is there. And it is also not fully non-covariant because coordinate dependent, because there is this covariance in that XA directions. So because of this, it is not very easy to see how to program this, either using extensor, which takes all components, which is like fully covariant, or xCoba, which is like fully coordinate dependent. So we'll have to be somewhat smart to keep using covariance in the transverse direction, that is along XA. So okay, so with this theory, now we are ready to see how to go ahead and do things in xAct. So the basic algorithm behind the partial covariance in the theory. So the idea is to notice that the four-dimensional metric is the one that was written above, can be written like this. The inverse of such a metric is this. Now the basic idea is to treat the unknown fields beta, V, U as fields in a two-dimensional manifold, of which the metric is GAB, and convert all the uh, uh, all the 4D quantities in terms of covariant derivatives and Christoffel connections of the two-dimensional transverse metric GAB. And this covariance, this partial covariance, was already achieved in this first paper by Barnish and Trossard. And the authors in this paper, they defined, for using certain notation, some additional fields KAB, LAB, and NA. KAB is essentially the R derivative of GAB. LAB is essentially U derivative of GAB, and Na is essentially related to U. It's some combination. Okay, so after this, the equations are solved using Bondi hierarchy mentioned above with radial expansion of metric G as given above. Once we do this, once we have readily expanded GAB, the raising and lowering is done with respect to the leading part of G, which is QAB, as you can see here. So all the raising and lowering will be done once all of this has been substituted with respect to QAB. Okay. So coding in xAct. So first we shall verify the results of one. And once we are confident of the expressions, we follow the Bondi hierarchy, but with the metric QAB, the leading part of the full transpose. In the above, all indices are raised and lowered with respect to in this particular. So there will be two mathematical notebooks. The one which I am using right now. Here we will be verifying the results of one, and the metric will be two-dimensional metric GAB, and in the next notebook the metric will be QAB when we actually solve illustrate the Bondi hierarchy. Okay, so with this let us set up the definitions. So yeah, so let's call the packages. So now there is this first command, preprint screen dollar indices. This, as we saw yesterday, this is to ensure that when Mathematica or xAct is doing the computations, which involves dummy indices which have dollars, this will like remove them when the output is shown to us. There is another command that one has to use, which is to set options for the two canonical. Yeah, so there is a command canonical which was very useful as we saw yesterday, but this has a specific feature which we do not want, and what is that feature? Let's see it by example. So before that, let's define two parameters U and R, which are the coordinates of the four-dimensional metric or of the space-time. These will enter as parameters in the two-dimensional theory that we are considering. So the idea is we define a two-dimensional manifold M2, which is two-dimensional, and with these indices, and it has a metric which has determinant +1, the signature is +1, and it has covariant derivative represented by CD, and we will print it as G. And note that there are extra dependencies on this, which is R and U. These are treated as the parameters. So let's run this. Yeah. So yeah. So okay. So this comment I already made. So now let's go on defining various tensors that there are. Beta, for example, is a scalar, so we will define it as like this. But we demand that it depends on the manifold M2 along with the parameters U and R. So let's do that. Now consider the following expression, EX1. So what it is saying is that we are taking the covariant derivative of beta with respect to A and then multiplying with GA. Now, if we do a two canonical, because this guy is so it's a covariant derivative, so it essentially raises the index and it becomes P. But now let's repeat the same exercise, but this time with a partial derivative. So you see what is happening. So it is saying that detected metric incompatible derivative, partial derivative. Obviously, it cannot do that. It cannot just raise that index. So in order to deal with to prevent Mathematica or xAct from doing such a thing, what we will do is we will switch off one of the features of two canonical, and that is that it is not allowed to use the metric to raise and lower indices on derivatives or anything else. Okay. So if I enable this option, see what is happening. So this time it did not It did not complain, and it also did not raise or lower itself. So this option we will keep. Okay, and there is another important pitfall to avoid, which is which I'll demonstrate now. So xAct is very good at identifying an invalid tensor expression and its manipulation. Above, we saw how it did not blindly raise or lower indices on partial derivative and showed us error and did not proceed further with computation. The command that checks validity of an expression is validate. Let's just quickly search what validate does. So it essentially checks the tensorial expression, whether the tensorial expression have any unknown heads or does not have an object, with invalid index structure. So actually the point is, this is the problem that we will see. So let me demonstrate it, how it actually is happening. In our program, we found that xAct fails to warn us or the user in the following case. So let's define this tensor UA, which is in the Bondi metric. So let's define a quantity EX. See, this is like product of two contravariant tensors, and this obviously is nonsense, because in general relativity this is not making sense, and xAct is not warning us also. But the point is, we can check it again and ask uh, next. So far so good. So if we use validate command, xAct does warn us. However, there is further subtlety. Let's take, for example, another example where we have UA and U. This is a perfectly nice object, and it's a scalar. But see what happens if we multiply these two. So once again, what it is doing, it is just collecting UA and squaring it. So this is again nonsense. Okay. But the more serious part is that if we take this expression and ask to validate, and this time it is not even telling us any error. Okay, so this is one very serious error which can lead us to like wrong computations. But fortunately, there is a way around this in the form of a couple of commands called put scalar and no scalar. So whenever we enter a scalar expression which is obtained by contraction of indices, like this is a scalar expression because there are a and a contracted, and we want to take powers of this such a scalar expression, what we have to do is we have to use a command called put scalar. So let me demonstrate it. So example 3, UA, and we call it put scalar. So what it has done is, see, it has made a bracket, and this time you see it has not done any nonsense. It's just cubing this scalar expression, and now we do no scalar. So what it is doing is UA, UB, UF. So we can let's say call x to the power 30. And then we say no scalar. So you see, there will be no problem with indices now. So this is a perfectly this. So this was the only subtlety that we found that encoding in xAct for this for the code. Okay, and with this subtlety out of our way, now we are ready to code further. So now let us define the other fields that I mentioned above. So there was this tensor scalar field B, and all of them depend on U and R. So these are the additional auxiliary fields that Varnish and Resort define. And there is this additional label which we can ask, which we are asking it to print as a, and etc. etc. Let's see, for example, we minus, let's say f minus g. So what it gives? So it is essentially giving us printing it as we expect. Okay, now Varnish Resort have set these k, l, and n to specific derivatives. For example, once there is this command called index set delayed. So what it does is it takes a tensor expression and equates it to another tensor expression. So on the left hand side, we have this tensor already defined, but this is equal to the partial derivative of g with respect to r. So now what you see, what will happen is if we let's say minus a minus b. So you see what it is doing. It is just taking replacing this expression with this. So this command index set delayed is like the usual command of Mathematica where we have dot and u rather than just the equality. So this is delayed in the sense it will not compute what is this derivative even if g was given. So that's the advantage of it. Okay, so then there are the other bunch of tensors which we can get from NKL, which have indices. Here all the indices were lowered, but we can have index down and up, etc., etc. So I'm defining further tensors for that. So with this defining the basic tensors, now let's define the 4D metric. So which, as we have already mentioned, we will think of it as comprising scalar fields b, p, and vector field u, and a metric field g. So now, yeah, so this is first part of our project to verify all the quantities given in Varnish and Resort. So the idea is to arrange the four-dimensional metric in a 3x3 table, and the third row and column carry an extra index which varies over takes two values. So this 3x3 table is essentially a 4x4 matrix in disguise. So, but this is however in our head and not what Mathematica knows. So we then tell Mathematica to compute the Christoffel connections, the Ricci-Riemann tensors, using the usual formulae, which we all learn in our general relativity courses, but in 3 dimensions. Like for example, okay, yeah, so this will become very clear once I move ahead. So now what we are doing is we are defining the components of the full four-dimensional metric. So first will be like GUU, GUR, GUR, etc. Let me just print it and show to you. So these can be rearranged in terms of a list. So metric list. So for example, the lower guy, it is GUU, GUR, GUB, GUR. So notice that this is a scalar because scalar in our M2 manifold, the two-dimensional manifold. This is also a scalar, but this guy has an index b and it's a vector. So that's how we have defined it. So GUA has a vector, etc., etc. So and similarly, we have inverse metric of this form. Okay, so now there is another command called make rule in xAct. So what it does is it okay. So let's take one simple example. Let's cut it out. Sufficiently complicated example. Okay. Let's take a more complicated example. Okay, so this we did run, but now let's take this one. So what it is saying is, so the syntax is like this: make rule, and then we have a curly bracket. Here, what we say is that whatever tensor you want to equate to another tensor which has similar tensor structure. So this will set this guy equal to this exponential of 2 beta v by r plus g of this guy. So let's just see the example. So I have called this rule GUU rule. So if I take this, so you see what is happening is that it is essentially replacing GUU with. So we can collect all these rules that we have made for all the metric components and call them another rule which is called Bondi rules, and the command is join. So this join essentially joins all the rules. And okay, some fancy way of just checking. So let's do this step by step. Maybe this one example.
Hi, Sitender.
Yeah, hi. Yeah.
Can you please take just one question is related to the current discussion? So,
I see. In LHS, in make rule, if you have two terms in LHS, one term in RHS, how to? Oh no. So you cannot have two terms. You have to have just one term. I think. Yeah, that's what I remember. Yeah. So
Suppose we have two terms, then in that case, how do we write it?
I think you can do maybe step by step. First define another tensor which has first define a tensor which is sum of these two terms, okay? And then equate this tensor to whatever you want in the RHS.
No,
So,
like since this is a tensorial quantity within make rule, it automatically takes care. Like if you like if you have some different indices and you replace this make rule, then it automatically works. But if I am not using make rule and use normal things like two terms is replaced by one terms, then in that case it only takes care the terms which you wanted to focus, but the other terms it doesn't take care. But do you know, is there any similar way like make rule it should work? I don't know, like
see, so let me try to understand the question. So you are trying to say, for example, here, if we have another thing.
Yes.
Okay, let's just try it straight away. Let's try it straight away. Okay. Let me just copy it and call it rule 1. Okay.
Yes.
And let's add another scalar. Okay. So GUR. Okay. So that's what it is. So it is saying that there are more than one terms. Okay. So you'll have to necessarily have one term. Okay. So now you want to see, you want to ask, how can we do this, right?
Yes.
So let's just try it. So what I was saying is the following. Let's define another tensor. Let's say G U R. Okay. It's also a scalar, right? So, and this depends on U and R. So we have defined this, right? So next what we will do is make rule. And this time what we do is this guy. And on the RHS, we have this. Okay. So let's call it some other rule. Okay, this rule. So now we have a rule which is assigning this new tensor to these two tensors. Okay, but we already know what GUU for these the rules are. So for example, let's GUU are. So now let's say Bondi rules. Sorry, G. I did not.
And this is slash dot, not double slash. Yeah.
Yeah, we can do. I mean, it can be done, but let's see. Okay. First, we have to give this thing, this rule. Okay, GUU R rule 1, so that it converts to this, and on top of this, then we give Bondi rules. Okay. Yeah. So this is what has happened. Okay. Got
Okay.
it?
Yeah.
Yeah. So that's I think it's a little complicated. Way directly you cannot do, but you define another tensor which is essentially sum of those two, and then you can make another rule which will do that for you.
Okay. Thank you.
Okay. Yeah. Sure. Yeah. So with this, let us proceed. Yeah. So let's do one simple thing just for. Okay. So what I'll do is I'll just. Okay, let's not do this. Let's just keep going because it might take some time. The point is the metric is in this form, and inverse metric is in this form. And then what we do is we just take this is like a 3x3 matrix. This is also a 3x3 matrix. And then we ask it to just multiply and do up our Bondi rules, do canonical matrix form, etc. And then we find that it's essentially inverse. So, and we do the other way also. We again find that it is essentially identity. So what we have, essentially we have managed to tell xAct that these 3x3 matrices are inverse of each other. And now the idea is, so these guys, these 3x3 matrices, we'll take them as metric, okay? And what we shall do is, yeah, so let me just read it. Thus, we have managed to put a 4-dimensional metric in a 3x3 table. Now the idea is to simply evaluate the Christoffel connections, all the geometric quantities, the Riemann and Ricci scalar using this 3x3 table. And I'll not show. So we all know that how given a metric, how to calculate the Christoffel connection. So we are collecting, yeah. So let list 1,1. Oops, sorry. Just okay. So here what we will do is the following. Okay. So this list essentially, this is essentially a list which contains the information about the Christoffel connections. The relevant part for us is these three indices. These three indices will take value 1, 2, or 3, which will denote the values of like three-dimensional Christoffel connections. These are some fake indices, but this one, for example, you can write any value to them. The only significance is that when the index is 3, for example, if C1 is 3, then we have to write here some of the two-dimensional index. Similarly, for C2, we'll have, if it is C2 is some third index, then we have to write A, B, or whatever this two-dimensional index. So let me just enter one example and then show to you. See this. Okay, let's say we want gamma 1, 1, 1. So it doesn't matter what the corresponding things are, 1, 1, 1. So it gives us the, this is like Christoffel connection G, sorry, gamma U, U, U. So you see, if I do a 2 here, it really doesn't matter. Nothing actually matters. This is part of the code. But when I have, let's say, 3 index here, then it is showing some error. So as I mentioned, it has to be, let's say, A. So suppose I want gamma A. This is gamma A U U. So gamma, you see there is this index A, and then UU index is there. Okay. Suppose I want it to be gamma B U U. So it does like that. Okay. So the idea is just take care of read it as you will do, like gamma 111, gamma 112, gamma 113, etc., etc. But only when the third index is involved, we have to bring in the indices that are on the two-dimensional. So let's say this B F G, for example. So this will be, for example, gamma 333. So now you see that there is this dummy index which Mathematica has given, but then there is this upper B and then lower F and G. Just look at this. So this is how we code, okay? So with this, we will have all the Christoffel connections. So there are some other things which are there, but we'll not go into them. Our idea is essentially to directly see if the results of varnish and Raswag paper are we can verify or not. Okay. So as I explained, this CC list has essentially all the Christoffel connections. So this 111 essentially means gamma UUU. So let's do one thing in detail, and then I'll just run others. Okay, so here we go. Oh, I suppress the output. So this is what gamma UUU looks like, and the so this G stands for capital gamma. Okay, and this is one expression which we get using xAct, and this is standing for varnish and threshold B. And what they give in their paper is sorry. Yeah. So what they give in their paper is this expression. So now the idea is we have to see whether these two expressions are same or not. So naively they do appear. I mean, we cannot naively see whether they are same or not. Okay. So what do we do then is we give the job to uh, xAct. So let's say to canonical. So what it does is it rearranges etc., and then it shows that the expression that we have and the expression that varnish or salt give, they are essentially same. So this we can do for gamma UU or gamma UUA. So this we can keep doing for all the Christoffel connection. So with this we can verify we verify that all the Christoffel connections are there. Okay. So let's not just keep running it. So this is all Christoffel connections. So we were able to verify them. Okay, so this is all the way to gamma ABC or ABF, for example. So having verified the Christoffel connections, eventually we want to use the Ricci tensor, which will go into the Einstein equation. So in order to do that, we once again using the metric. So Ricci scalar is essentially sum of 4 terms. So and we calculate them individually. This is part of CC list. Just a minute. Okay. Okay, no issues. The point is the following. So this CS, let's search for it. CS. Yeah, okay. Unfortunately, we'll have to run all of this. But let's see. Okay, so there is some internal thing which had to be done. So once we do that, now we can go to the the Ricci. Yeah. So we calculate the Ricci. So now using our expression of CS rules, it's a little involved, but just okay. Sorry, actually everything had to be run. So there is some internal thing, internal code which had to be run, which I did not. Excuse me for this. Actually, it would take a lot of time if I explain this. So, okay, fine. Now with this, we are ready to define all the Ricci tensors. So let's say RUU. So this will be, once again, as I have said, if there are if the third index is not there, we can put anything in the first two guys. So oh god. I should have run everything. Let's run everything. Okay, great. So I think now it's working. Yeah. So for example, you see you're faced with this Ricci tensor, and this is a huge expression. And then you have RUR, which is also relatively shorter. Oops. Then you have RUA. Notice here we have 3 index, so we'll put A here. And these are all RR, RA, RAB. So this is the final Ricci tensor. So now in the Varnish Resort paper, they do give the expression for Ricci tensor. So which we just write in the xAct. And yeah, so for Varnish Resort, we do give the Ricci tensor. And so RUR for Varnish Resort is this. So let's just check one of them. Yeah. So this is the RUU that we had. This is Varnish Resort. If you just run it, then they show that it is 0. We did not run all of them, but as I am saying, all of them get verified. So essentially, we have verified the Einstein equations given in the Varnish Result paper. So this sets up the thing that everything is fine. Yeah. So this is so I'm done with the first part of this verification. The next part is actually solving the Einstein equation. So yeah, before this, are there any questions? And how much time do I have?
Around 10 minutes.
Okay.
Any questions from the audience?
Okay, seems like
okay, Sitender, maybe you can just continue.
Yeah. So okay, so let me share my second thing. Okay, so now we have used Varnish Resort, and then there are. Can people see this? Is it visible?
Yes. Go ahead. Yes.
Okay. Yeah, great. So now let me first which color? Yeah. So now, so having solved for the Einstein, I mean, having found that Einstein equation, etc., are correct. Now we go on to see how do we actually solve in the Bondi hierarchy. So there are certain notations that I need to use, and this we will follow from the paper by Mark and Celine, where they use this compact notation: CAB is essentially CC, CAB, D is essentially CD, etc. And they also the traces are denoted by without any indices. C is QAB, CAB, D is QAB, DAB, etc., etc. So we shall follow the notations there. So let's set the directory. Let's run extensor xAct. Once again, the standard thing which I defined earlier. So as I mentioned in the beginning of the talk, this part we will use the metric as Q rather than G. So there are some rules that we define that partial derivative of R is 0, for example, partial derivative of U is 0. And once again, we define all our metric, all our quantities. But this time, G has been defined as a symmetric tensor, not as metric, okay? And because we will expand it in powers of R. So this is to be noted. And similarly, in Mathematica, capital C, capital D, and capital E are already built-in functions, so we cannot use them for the fields. So what we do is we essentially use small indices for them, but we can print them as capital as we want. So I define them. And G4, G5, and G6 are the expansions of the inverse metric at order R4, R5, and R6. So for example, if I input CAB like this, it is CAB. Similarly, there are the traces, as I mentioned above. So the traces I denote by C0 because these are scalars and represent them with capital C, capital D, capital E, capital F, etc., etc. And the trace-free parts of all the objects are denoted by curly D. This I explained in the beginning part of the session. So now what we do is we define some trace tools and some scalars. And then there are certain identities which Mark's paper gives for which pertain to this the tensor C. And then we had earlier seen that the metric condition essentially relates DAB, for example, D minus A minus B. See, this is essentially DAB, but we saw earlier that DAB is related to other quantities because of the determinant relation. So let's see that. So this was the relation, okay? So this is what I have essentially told Mathematica to do. And then there are this index set. So what it does is it takes some quantity and it sets it to certain quantity, okay? So there are some definitions which the scalars will be equal to, and I have quoted here. Now comes the main part. So here what we see is we make a rule for expanding the metric and the inverse metric, and together I call them metric expansion, full metric expansion. So for example, if I have the metric G minus A minus B, then if I ask it to do metric expansion, so it will do this thing. And similarly, if I have AB and I ask it to do IMET, so it will take into account those things. Now the idea is to expand all the fields. So we expanded metric. Now let's expand the beta. So beta is expanded as beta naught, beta 1, etc., etc. Similarly for U, so U is essentially U naught, U1, U2, U3, and there are some log pieces which we will find that they go to 0. Now, so having expanded all the fields, the U's, the betas, the metric, and the V. Okay, so we will not require V in this lecture. So the point is the first equation that we have to solve in the Bondi hierarchy is this RR equation, as I mentioned, and the second equation is at RRA. So this is the expression for the Ricci tensor. Now what we do is the following. We take this RRR and do substitute, for example, okay, let's do it step by step. I think I'll be done in 5 minutes. So let's take this RRR. So it gives us the expression in terms of the upper metric and the lower metric and beta. So what we will ask it to do is, let's say, metric expansion. Oops. So what it will do is it will expand the upper and the lower metric, but still you see that there is a beta here. So what we'll ask is to beta expansion. So it puts that thing again. So now this is the equation. And similarly, we do this for RRA. We expand also in, there is this U also there, which we expand. And then there is this expression for the inverse metric, and it is given like this. And we set them equal to this. Okay, so having in our hand all the definitions and expansions correct. So okay, this was just an example about how in the limit r going to infinity, the series function behaves. So let's recall one thing. Suppose we have a function f of x, x naught, x 1000. So if we ask Mathematica to give us the coefficient of the second order term, so it is giving us that, okay? But notice that so this expansion is about x equal to 0. So the power which we want and the power which it gives is essentially same. But this is not the case when we have r going to infinity. For example, let's take example a little slowly. So there is this quantity GAB, the inverse metric. And you see this is expanded in powers of 1 over r. So now if I ask to do this series for this test, r going to infinity and keep terms up to order 3. So it is not r cubed actually, it is 1 over r. So that's the point I wanted to mention. In the limit r going to infinity, it automatically assumes that the expansion is done in powers of 1 over. Okay, so that's the thing. So if I, for example, ask it to give me the coefficient of 5th power in 1 over r, so here we go. This is the thing, and it gives that. So this was one technical point. So with this, now let's try to do the thing for this the RR expression equation. So I ask it to expand, let's say, to order minus 1000. That means r raised to power 1000. There is no such term. Similarly, you can keep verifying to, let's say, 100 or 10. There is no such term. 8, no term. So eventually you will come to minus 1. There is no such term. That means Einstein equation is getting satisfied automatically. At order 0, once again, there is it's getting satisfied. Order 1, it's also getting satisfied. This happens till order 2. But then once we come at order 3, what we find is that this equation gives us 4 beta 1. But beta 1 is the coefficient in expansion of beta. So in order for the only way for which the Einstein equation will get satisfied is that beta 1 must vanish identically. So this is what Professor Amitabh mentioned in his lectures, and in particular today. So with this, having found this constraint, we set beta 1 to 0 and make a rule out of that. Now we go to next order. And this time our order 4, and there are various manipulations one has to do, which I do not have time to explain. If I do this, what I find is that at this order, the coefficient beta 2 appears along with the C, the most important tensor, as Professor Amitabh has been mentioning, the C. So once again, for this to be satisfied, this must be equal to 0. So what it tells is that this beta 2 must be equal to CC by 32. And that's what we do. Similarly, we can keep going higher in order. And then we find what is beta 3. So beta 3 will be equal to CD, so on and so forth. So similarly, Okay, so point is there is just only one thing left, beta 4. So let's also do that. So once again, you see that at this particular order 6, we find that beta 4 is coming, and it is related to all the other fields that appear, and then we make a rule out of it. Okay, so now in final 2 minutes, I'll explain how we repeat the same process but with RA equation. So we find that at particular order r equal to 1, we get this equation. And then this essentially tells us that u1 is essentially equal to del A beta naught times this quantity. So similarly, we go another order, we find u2, but then this expression is complicated. But using xAct, we can convert all the partial derivatives into covariant derivatives, and then we get a simple expression. And then we can invert this equation to get what is u2. And we find that all of this matches with what has been given in the compares paper. So I think from here we can keep going on like this, demanding that the Einstein equations are satisfied at each order, and we get various solutions. Of course, more technicalities appear as we go along, but the idea is clear. We keep moving brute force. So yeah, so that's it from my side. Like, there are various other equations, and we can keep repeating this procedure. There will appear many identities that we'll have to take into account, but that's all. So and yeah, and in particular, when you go and solve for this RUU equation, there you'll find that the Bondi mass loss formula appears for the curved spacetime. So that's the expression actually I was dealing with. There are a lot of complications there, and but I think those can be managed, and this is part of ongoing project. So yeah, so that's all from my side. If there are any other questions, I'll be happy to